Hi, everyone. In this video, we're going to be looking at more examples of identifying trees, and so seeing whether a graph is a tree or not. So our original definition of a tree was a connected graph that didn't contain any circuits. But the problem is it's not always super easy to determine whether or not a graph has a circuit. Maybe you can just look at it, but if a graph is drawn in a really gnarly way, then it's not immediately obvious. It's not clear. And so we have these alternate criteria for when a graph is a tree, some of which are very computationally helpful. For example, we have that if there are n vertices, there must be n minus 1 edges in order to be a tree. So this is what's in practice very useful for us. So for this first graph here, take a second and think about it. Hopefully you've paused the video. This is not a tree. Why isn't this a tree? Well, first of all, there's many different reasons. One reason is we have a circuit, E, A, B, H, E. That's a circuit. So EG, so we have E, A, B, H, E is a circuit. So as soon as we have a circuit, we don't have a tree. But maybe you couldn't see that circuit. That's fine. Well, another thing we can do is we can count the vertices. So number of vertices is, well, 1, 2, 3, 4, 5, 6, 7, 8, 9 vertices. So we have 9 vertices. How many edges do we have? So in this case, that tells us that our n equals 9. And so n minus 1 would be 8. 9 minus 1 is 8. So we need exactly 8 edges, or we're not going to be a tree. So how many edges do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9 edges. So we don't have, but n minus 1 is 8. So we don't, these are not the same number, and that means we are not a tree. Now, I also didn't verify that this graph is connected. It is. So for example, from E, we can get to F, D, A, B, H, and then we could go from B to C, C to I, and from B to G. Okay, and so we can find everything is connected. We can always find a walk from every vertex to any other. So this is not a tree. Let's move on. Again, I've drawn it in kind of a gnarly way. It's kind of hard to tell whether or not this is a tree. So let's first make sure it's connected. So I can get from F to H, from F to D, F to J. I can also get from F to A to B to I. I can get from F to A to E to G. So that means we are connected. But notice, I can also get from G to D. So I can get right from F to D, and I could also go from F to A to E to G to D. So we, once again, have a circuit. F, D, G, E, A, F. Another thing is we can think about is we have more than one path from F to, say, G. One of them is F to D to G, and the other is F, A, E, G. And so by doing one path from F to G and then the other one in reverse, so one from G to F, we get a circuit. But again, let's say you didn't find that circuit. Let's say you didn't notice it in all this mess. That's fine. Then what we can do is we can count the number of vertices. So counting this, we'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so I'll ask you, if we have 10 vertices, then how many edges do we need to have in order to be a graph? So we need n minus 1 equals 9 edges, right? If n is 10, then n minus 1 is 9. Let's count. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 edges and 10 vertices. That means we're not a tree because we don't have exactly n minus 1 edges. So we are not a tree. And this is pretty cool, right? Even just counting, if I know that I don't have n minus 1 edges, if I have more or even less, if I have more than n minus 1 edges, I automatically know that I'll be able to find a circuit, automatically. Now let's move on. So this one, also drawn in a kind of strange way, but let's make sure we're connected. So let's say I can go from A to B, A to B to D, I can go A to B to E, A to B to F, I can go A to C to H, I can go A to C to G, A to G to J, A to, and then I can also go A to I. So I can get from A to any other vertex, which means I can get from any vertex to any other vertex, which means we are connected. Well, can I find any circuits? Well, I've got this sort of thing going on. So I can go from A to B, and then I can go B to F, and A to I, but these don't start and stop on the same vertex, so it's not quite a circuit. So let's and this is gonna be a bit tedious, but let's delete every edge and see if we have a bridge. So if I delete GJ, that disconnects me, so that's a bridge. If I delete CH, then that disconnects me, that's a bridge. If I delete CG, then I'll have two components. I've got this component and the rest, so that's a bridge. Similarly, if I delete AC, then I've got two different components. I've disconnected, so AC is a bridge. AI is also a bridge that kills any connection to I. AB is also a bridge because now this and the rest are sort of their own components. If I delete, BD, that makes D isolated. Similarly for BE, that makes E isolated. And if I delete BF, that makes F isolated. So deleting any vertex or deleting any edge disconnects my graph, so disconnects the graph. So every edge is a bridge, and that means that this is a tree. Now, every edge is a bridge, which means, in other words, this edge AC is the only way to get from A to C. If I had some other way to get from A to C, so maybe if I had an AJGC, then that would be a circuit. So if I had another way to get to C, say another path to C, then C wouldn't be a bridge because if I deleted it, I could go on the other path. Okay, and now let's do our count our vertices and edges. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 vertices. Now the number of edges, when I count that, I get 1, 2, 3, 4, 5, 6, 7, 8, 9 edges. So if n equals 10, n minus 1 equals 9, we see I have 10 edges, I have one less edge, so I have 10 vertices, one less, 9 edges, so that means this is a tree. And I didn't really talk about bridges for these other graphs, but notice, if I take any of these edges that's part of this circuit from this previous example, and I delete it, I'm still going to be connected. I can still get from F to H, F to D, F to A to E, F to E to C, F to A to E to C, F to A to B to I, and I can go F to D to G. So I can get and F to D to J. So I could still get from everywhere. So that means EG was not a bridge. So I didn't talk about bridges for these ones, but for these ones, we have edges that are not bridges. Finally, this one, which looks like even more of a mess. So let's confirm that it's connected. So I can get from J to C. I can get from J to C to E, but it looks like I can't get from J to I or anywhere else. So this graph isn't actually connected. But if I draw an extra edge here, it should be. So now I can go from J to C to I, then to B, A, F, H, J, K, D. Yes, I can get everywhere. Now it's connected. So I encourage you to pause the video and check a little bit more carefully that once I draw this extra edge, my graph is now connected. And so now this is really messy. I don't even want to bother trying to find any circuits or anything. I'm just going to go straight to counting my vertices and edges. So for vertices, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 vertices. And my number of edges is, well, let me count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I have 11 edges, which means I don't have one less edge than I do number of vertices. So that tells me that this is not a tree. I would have needed 10 edges. And so I encourage you, I'm not going to do it. I encourage you to pause the video and try to find either an edge that isn't a bridge or a circuit within this graph. Okay, that's just extra practice for you, but that's going to be all for this video.